Okay, so I'm showing you the trace of this basically the circuit I went through in class today. Okay. And if you're interested in knowing what the circuit is, it's right here. I have a resistor here, and then I have a little box in which I can vary the inductance. And I'm measuring the voltage across the resistor. And my R and the L, my L is small right now. So the combination of omega times L is small. So the phase shift is small. So I want to show you how I can vary the phase shift between the power supply voltage and the voltage across the inductor. So in this trace, the yellow is the power supply voltage, and behind it is orange is the voltage across the resistor. So what I'm going to do is I'm going to vary the frequency of the signal. And I'm going to have to change my time scale. And as I change the time scale, I think what you'll notice is basically the shift in the peaks. Do you see how the peaks shift? And the thing is that as I make the frequency greater, then the voltage across the inductor is going to be greater. And so the inductor is going to dominate, and we're going to approach a 90-degree phase shift. Now I'm at 40,000 hertz. Notice that there's a phase shift of almost 90 degrees between the resistor and the power supply. Can you all see that? The little orange one? That's essentially a 90-degree phase shift between the two. And as I reduce the frequency down to 0, the resistor will dominate in the circuit. So Morgan, in this particular circuit, because I just have an inductor and a resistor, 90 degrees will be the maximum. In fact, if I had a resistor, a capacitor, and an inductor, the phase shift will go from 90 degrees to minus 90 degrees to plus 90 degrees. So that's the range. It'll go from minus 90 to plus 90. So when the frequency is very high, then the phase shift will approach 90 degrees. Because if you remember, the equation I wrote for the phase shift was the inverse tangent of the reactance of the inductor divided by the resistance. And so the numerator has an omega in it. Let me write it on the board. Oops. I think it's okay. So I had written on the board that phi was the inverse tangent of x of L over R. X of L is omega times L. So as this goes to infinity, then this goes to 90. And as this goes to 0, then this goes to 0. And you clearly see that here. Unfortunately, we could not purchase you these nice scopes. Because if we can use these nice scopes, in the last lab, you can actually look at the phase shift. But you have these guys, which only have one input. Okay, that's unfortunate. So let me reduce the frequency. And you can see the phase shift really going towards 0. Like now that we're at about 1,000 hertz, You can tell they're not even separated. That phase shift is so small. It's almost zero. If we had a better scope, we could probably measure it. Okay. And then next time I'll do a circuit with the R, the L, and the C, and I'll try to scan over the entire range from -90 to +90 with the R, the L, and the C. Okay? So I just wanted to show you that, which is kind of interesting. Unfortunately, in the lab, you're not going to be able to see this because of the scopes you're given. So in the lab, you're going to just use the scope to monitor the supply voltage. Okay? All right. So let me switch back. Oops, I messed up. Sorry. Okay. Okay, that's better. So this is our lab. It's only a 20-point lab. The goal really of this lab is really to get you to more familiarize with the scope. You're really not going to learn every single feature that a scope has in our course just because of the scopes we've given you. There's one feature in that a regular scope has that these don't have that we can't use. And so normally there's actually another part in these experiments where we have you measure basic measurements in these circuits. So really the big goal is to learn how to use a scope. We're going to measure the capacitance of a capacitor and the inductance of an inductor in the circuit based on some of the measurements we obtained from the scope. Now, in this lab, the inductor that we purchased is quite small. We purchased that inductor so that we can use the same one for the last lab, but that was a mistake because the inductor we purchased does not allow you to do part 3. So skip part 3. Okay, I'm going to type it in here. Okay, so skip part 3 of lab 7 because you just can't do it. 3. So there's 3 parts, and just the last part. Although I'm going to go through the theory of it because the theory is interesting and it kind of sets up the RLC circuit with the AC power supply. So I'm going to go through it, and I'm just going to look at the behavior of the circuit. I'm not going to go look at all the details. So there are 3 parts. The third part we're skipping, and the first 2 parts it's not too complicated. Okay. So let me go through this lab. So I'll talk about the lab, then I'm going to talk about the LC circuits in general that I skipped in chapter 32. And then I want to do the RLC. That's going to take me a while. Okay. So let me just quickly go through the 2 parts of the lab here that you can see. Part 1, you're basically setting up this circuit. And then part 2, you're replacing the capacitor in the circuit with an inductor. That's really it. Okay. And there's a little bit of theory, but there's not a lot of analysis. I know that Lab 4 had a lot of analysis. Lab 4 had a lot of analysis. This one doesn't have as much analysis in it. And in fact, the uncertainty calculations are a lot easier in this lab. So you should be able to get through this pretty quickly. But it's really important that you understand how to do this lab. If you're getting poor results in this lab, you got to contact me just to make sure that I know that things are working. I had a couple of people in the DC circuit lab, which I'm still grading, got poor results, and they just left it and didn't contact me or anything. And, you know, I just wondered, does the student care about what they're doing? Okay, so it makes me question that, because how do I know the equipment's not working if you're getting poor data? So I need to know if you're getting poor data. You got to tell me, okay? So don't wait till the last minute to do this lab. I mean, it really doesn't take a long time to do it, but don't wait till the last minute, because that way, if there's an issue with it, we can figure out a way around it. And I've actually had set up some Zoom meeting with students to help them get through some of these labs. So please, if you have any problem, just don't hesitate to ask for help. Okay. All right. So let's look at the first part of the lab, where we're actually going to look at RC circuits. I know we covered RC circuits a while ago, but this lab is perfectly set up for us. Magnify this. This lab is perfectly set up for us to do this measurement. So let me draw the circuit on the board. So we have a power supply, and the power supply is going to be a square function, because if I use a DC power supply and you try to measure things on a scope, you're going to quickly reach steady state, and you're just going to get a horizontal line to look at, which is really boring. We'll have a resistor, a capacitor, and you're going to monitor the voltage across the capacitor. So what is our goal? The goal is to measure and to determine the capacitance value from quantities that are measured using the scope. And you're going to do this particular measurement at 3 frequencies. You're going to set this at 100 hertz, 250 hertz, and 500 hertz. So you will be using that little signal generator that you used for doing the oscilloscope quiz. You're just going to set it to set the signal generator for a square pulse. It's kind of cool though. The signal generator can do square pulse, sawtooth, all kind of interesting signals, and it even does the EKG. No, we're talking about part 1 right now, Morgan. I'm going to talk about part 3 last. So the part I'm showing you in the corner is part 1. Okay, the part I'm showing you in the left-hand corner of the screen is part 1. So this is the setup for the lab, and so you're going to have your signal generator, your resistor, and you're going to measure this. And you're going to observe the voltage as a function of time on the scope. And we've talked about how the capacitor charges up. It charges up exponentially. But if I have a square pulse, once I turn the power supply off, the capacitor then will discharge and then charge. That's why I put a picture. Okay, etc. I'm bad at drawing. Okay. Yes, you do have a capacitor in the kit. It should be 4.7 microfarad. If you don't have a capacitor in the kit, I need to know right away. Okay? You should have a capacitor and an inductor. The capacitor is blue. And it should say 4.7 microfarads. Yeah, I'm going to get to the inductor in a minute, okay? I'll get to that. Oh yeah, it is blue. It is black. Oh, yours is black? Okay, mine's blue for some reason. Does it have blue writing on it? Okay. As long as it's 4.7 microfarad, that's fine. So, from information we get on here and the measured resistance, we're going to measure the capacitance. Okay. So we know that the voltage across the capacitor, and I'm going to call this the power supply voltage. If you don't mind. You want to use different. You want to use delta V sub B. That's fine. Okay. Yeah, I'm sorry, Marty. Mine was blue. My capacitor was blue. It's going to be delta V sub S times 1 minus e to the minus t over RC. Question is, at what time is the voltage across the capacitor 1/2 its maximum value? In other words, when is the ratio of delta V sub C over delta V sub S equal to 1/2? This is T subscript 1/2. This is the time in which this ratio equals 1/2. I'm going to solve that. I'm going to solve for that. Of course, I can cancel out the minus signs. And then I take the log of both sides. And I'm going to cheat now. I'm going to get rid of the 1/2 by doing this. And then I can solve for C. Let me rewrite this. I'll write it over here. The reason we write T subscript 1/2 because, again, this is the voltage, the time it takes for the voltage to be 1/2 its maximum value, which is 1/2 the power supply voltage. And you see this notation if you've ever talked about or if you've ever learned about radioactive decay. When you talk about the time it takes for the material to decay to 1/2 its value, you talk about half-lives. So, you're going to measure the time it takes for the voltage to be half its maximum value. So you can either measure this time or this time, it doesn't matter. What do you mean? I'm not sure I understand. Should it be flipped? Isn't this true? Okay, that's what I did. That's what I said. I'm going to cheat real quick. That's why I got rid of the minus sign. So originally I had this, and I said, okay, I'm going to cheat real quick. I'm going to rewrite this. Okay. Yeah, you'll see that a lot in this class, and you see it in the class when you talk about radioactive decay. You see that the trick being used. Okay, just to save. I don't have a lot of board space, so I have to use shortcuts. Oh, I forgot. The minus was supposed to be here. I screwed up. There's too many minus signs. It was originally like this. Right? This is what it had originally. This minus sign is this. Okay? I've been going back and forth on that one too many times. I've made a mistake. Sorry. Okay. So, this is what we have for C. By the way, see, if you see the theory section, in part 1 there, on the left-hand part of this left-hand corner of the screen, this is what I want you to derive. And when you derive this, I just don't want to see a bunch of letters there without any explanation. I mean, imagine if your textbook had just a bunch of equations with no explanation. How hard is it to learn? You got to remember that you're not writing to yourself and you're not writing to me, but you're writing to a peer in a classroom who would be able to learn from what you write. Okay. The hardest thing about learning how to write labs is to not write to yourself. That is the hardest thing to learn. I know, because I've gone through it. Yeah, but I don't want a lot of explanations. I mean, this short phrase is saying what you did. Okay, I don't want it to be a long discourse. Right? Just you put enough here, and it could be a phrase that says tells the reader what you did. Does that make sense? Because I don't want you to spend a lot of time writing along. I don't want it to be like a textbook, but I want it to be so that someone can quickly understand what's going on, what the letters mean. Okay. No, you can just say dividing by. I can say when I go from here to here or from here to here, just say take a log of both sides. That's it. Okay. So you would write down. And you can do my algebra thing that I skipped, but it's okay. Because you guys should be able to figure that out. Okay. How do you know that this first line is true? Well, I am going to assume you start from this and then say, let's look at when this ratio, the ratio of V over Vs is 1/2. Right? Okay, right? We want to look, because our goal is to look at the signal when V equals V 1/2. And then we're going to measure this time, because that's, right, you're going to be, what your goal is to derive the working equations. Now, I don't want you to derive this, unless you really want to, okay? Most people are not going to want to derive this. Okay, but let's say this is our starting point, and then you say, oh, since I'm going to measure T1 half, I want to derive the equation to be using to do my calculations. So all you're doing is deriving the equations that you're using to do your calculations. That's it. But I don't want you to start from scratch. I don't want you to have to derive this. I'm just trying to save work for you guys. Okay. Okay, so are we clear on what's expected from you on this first part? You're going to do it at 3 different frequencies. So on the oscilloscope, I'm trying to understand. I guess which oscilloscope are you talking about, Morgan? Are you talking on this plot? There's V sub C. It's the voltage across the capacitor, because that's what we're measuring. I'm referring to this because that's what we're going to be measuring. V sub S is going to look like this. And unfortunately, you can't see them both. Yeah, this is the power supply. Unfortunately, you won't be able to look at both of them at the same time. Unless you take the lead from here and move it here. Then you can see, but then you have to switch between these 2 points. All right, if you take the lead from here and move it to here, you can see the power supply. If you move it back, then you can only see the capacitor. But you can only see one at once. And that's all we have. We have a $20 scope, so that's all we can do. That's all we have to live with. Okay. It's unfortunate because if we had the nice one that I'm showing you, that I showed you, you can actually see both at the same time, which is awesome. And I think last week I used that scope to look at the 2 square pulses in one of my lectures. Okay. Any other questions on this? Okay. Now, part 2, we're going to replace this with the inductor. And you're only doing one frequency. And I haven't emailed you the new version of this. And the reason why I had to make a new version is because this inductor was too small. This inductor is 1.0 millihenries. I'll show you the inductor in a minute, okay? When I did this over the summer, when I designed the lab, I designed it for 10 millihenries. And so then we would use 500 Hz. If you do this lab at 500 Hz, you won't be able to do it because the decay is so fast. Okay, so you need to do this at 5,000 Hz. All right, just remember, do it at 5,000 Hz. And I told the other class many times because I want to make sure that that's clear. Okay, so you set this to 5,000 Hz. This thing goes up to much higher than 5,000 Hz. Okay. And you're going to do the same thing. The goal then here is going to be to determine L from the quantities that are measured on the scope. And your V sub L is going to look the same. Your V sub S, and these should be deltas, I apologize. And I told you earlier when we started on this, when we talked about potential differences. Initially, people write delta V's, And then when you get to this part of the course, they stop dropping the deltas. Right, they start dropping delta. You see it even in your book. Okay, so let me show you what this. Let me show you what the inductor looks like. Really, you can see again, it's the same picture for the circuit. Oh, and your resistor is going to be 100 ohms, by the way. Okay, so let me switch cameras real quick. It means I have to disconnect my microphone. Okay, so I'm going to show you the circuit that I built. This is not too complicated. I'm going to try to keep my hand steady so that you can see a clear picture. You see the item on the left? Hold on a second. You see the item on the left? Yeah, they're not. The one on the left is not a resistor. The big looking resistor is an inductor. Okay, so you should have one like that. Okay, so the one on the left is the inductor. The one that looks like a big resistor is an inductor. It's black, it's brown, black, red, and gold. It is a 1,000 microhenry inductor. Same thing as 1 millihenry. Okay? If you measured its resistance, it would probably be, I think it's around 1 ohm. That would tell you something's wrong. Or no, it's 3 ohms, I think. That would tell you something is wrong. Okay? When you did the circuits lab, if you tried to use that, you would have noticed that something's wrong with that because it's only like 3 ohms. So this guy is the inductor. Okay, this one right here, the big one. And the one on the right is the actual resistor. Please let me know if you don't have that big inductor. So in your kit, there is another resistor that's this big, that's gray. That's for the last lab. Okay, that's for the last lab. There's a resistor that's gray, and that'll be for the last lab. That's like a 1.2 ohm resistor. Okay, and again, let me know if you don't have that inductor, because I have to get that to you. Otherwise, you can't do the lab. Okay. All right. Is everyone clear then that the one on the left there is the inductor? Okay, good. You have the inductor. I just want to make sure everybody has the inductor, so they can do the second part of the lab. Okay. And if you don't, then let me know. We'll get one to you right away. Okay. All right. Because I did have a couple questions earlier in the semester about what is that big resistor for? There's 2 of them, right? You should have a gray one in your kit. That one's a 1.2 ohm resistor. Okay. Let me change back. Oops. And I want to plug in my good microphone. Okay, so part 2, there's also a theory section. And we're really going to do the same thing, but we're going to do only one frequency in this case. In the first case, we did 3 because I want you to see if the frequency makes a difference. And in this particular case, just because I just want you're doing the same thing again, essentially. I'm just having you do it once. Okay. So we need an equation. We need to derive an equation for the inductor. We need to do a similar derivation for the inductor as we did for the capacitor. So let me go back up to the board. And this works for the capacitor, but what works for the inductor? Well, we know for the inductor, that the current is equal to, or not the inductor, but the RL circuit. The current is equal to I max or I battery or I supply, whatever you want to call it. Let's call it I max. Times 1 minus e to the minus r over LT, where I sub max is the power supply voltage over the resistance. But we know that the voltage across the inductor, because you're going to be measuring the voltage across the inductor. Is given as L di dt. Let me go back to my other marker because the other marker is a little bit better. I got to take the derivative of this with respect to time. The first term is a constant, so that disappears. When I take a derivative of this, I want to get an R over L. Then I still have my I max, which is the power supply voltage over R. And so this is going to give me that. Okay? Oh, it's too far up, sorry. Is that better? Okay. I'm going to make it a little bit more. I'll fix a little bit more. Okay. So, what are we going to do? I'm going to ask the same question. At what time is the voltage across the inductor 1/2 its maximum value? Which means that I want delta V sub L over delta V sub S to be equal to 1/2. Guess what? I'm going to go through the same machinery. I'm going to take the log of both sides. And oh yeah, this is T 1/2 also. When this is 1/2, then I'm going to call this T 1/2. Let me come over here. I wish I had a bigger board. And then I'm going to do the same trick again. And so I'm going to solve for L. You have this working equation and this working equation. So, you know, when you do your air, by the way, you're going to be doing air propagation. This one's going to be easy. That one's going to be easy. Natural log of 2, just pretend natural log of 2 is exact. It probably isn't, but let's assume that's exact. Okay, because the air is factored into this thing anyway. Right, the air and knowing whether that ratio is 1/2 is factored into this thing. So when you do the air analysis, just do the air analysis on these two terms. Okay? So that's it. And you'll only do this, you'll do this at one frequency, and you'll do the first part of 3 frequencies. Remember, for part 2, it's 5,000 hertz. For part 1, there's 3 frequencies, 100, 250, and 500 hertz. Really, that's it for the lab. Questions or concerns? We're skipping part 3. Yeah, just measure with the measure R. So the question is, do we measure R? You measure with the multimeter. I'm not sure what you mean by is T given. You got to measure T. You mean T1 half? Yeah, how do you do the air propagation for T1 half? How well can you measure the time? Well, here's a grid, right? Each grid is 0.2 units. Okay. So what does that correspond to in time? Well, it's 0.2 times the time scale. How well can you measure, how many grids can you, to within how many grids can you measure a time? My guess is at best, you can measure to within 0.1 units. Right? The thickness of the trace is about half the spacing between the 2 lines on the grid. So I would say my uncertainty and my time measurement is to 0.1 units. Yeah, so you take the 0.1 units and multiply by the scale, whether you're measuring voltage or you're measuring time. In this case, you're measuring time. You're not really measuring voltage. You're just measuring time. Okay? 0.1 times the time scale gives you the uncertainty. Does that make sense? Yeah, I wouldn't go below that. Some people try to go below that and get the extra digit. I'm not comfortable with that because of the width of the trace. Okay. If the trace was even, I mean, even when we do this in class, when we do it on ground, the bigger scopes, the actual trace is thicker than what you see on the scope you have. It's much thicker, and you can clearly see it. Oh yeah, there's an uncertainty just because of the thickness of the trace. It's a little bit harder to see it on here because the grid spacing is small, and then so is the trace. The trace is small too. Okay. So that's a good question. I mean, it should be 0.1 units. You should always assume about 0.1 units. Okay. I have a hard time. Of course, if you can expand your trace, right? The more you expand your trace, the smaller your time scale, then the better your resolution. Does that make sense? If you can expand, if you can expand the trace on your scope and make the measurements, that's the goal. Then 0.1 units times a smaller time scale will give you a smaller uncertainty. And then when you expand the scale, it's easy to measure things when you expand the scale. Okay? That's a good question. All right. So I want to talk about the LC circuit. I skipped when on Monday's presentation, flipped presentation, I guess I would say. Okay, so let me go to the PowerPoint slides for chapter 11. I'm sorry, not chapter 11. Chapter 32. So I want to look at the LC circuit, and what I want to consider is the following. Okay, let's consider the following circuit. Let me erase the board, because my goal at the end is to do the more complicated circuit. What we're looking at is transient responses, but I want to look at this particular circuit. Suppose I have a power supply, and I have a switch here, an inductor, a capacitor, like that. I close the switch. What happens? Well, at t equals 0, this capacitor acts like a wire, and the inductor acts like an open circuit. So all the current goes through the capacitor, none of it goes through the inductor. As the capacitor charges up, the current in this guy decreases, and the current through L increases because di dt is decreasing. And as I go to t equals infinity, or when I reach steady state, then the capacitor is fully charged. No current goes through here. All the current goes through the inductor because the inductor now acts like a wire. So let's say the capacitor is fully charged, and then I open the switch up. Let's assume ideal inductor. Okay, that means when I open the switch, there's no resistance here. That means there's no energy lost. Well, I got to say one more thing. The charged particles in the circuit are accelerating all the time. And so anytime a charged particle accelerates, they do give off radiation. Let's pretend that radiation is 0. Let's say they're not radiating. Or their radiation due to the acceleration of the particles is negligible. That means that no energy will be lost in here as the capacitor discharges. Once I open this up, the capacitor will discharge through the inductor. So as the energy is lost from here, it actually goes into the inductor. The inductor now starts storing energy. Remember, the inductor, the energy stored is 1/2 Li squared. So this loses the energy, and then this gains the energy. Once this capacitor is fully discharged, all the energy is in here. Guess what's going to happen? The energy is going to go back to here. Since no energy is lost, the energy is going to go back and forth forever as long as we have no resistance. It's like the mass on a spring problem, where you have energy being converted between potential and kinetic. So what does this mean? Well, let's take a look at the total energy. The total energy at any time, since energy is being transferred between the two, the total energy is just and if I take the time derivative of this, if no energy is lost, then this is 0. Let me use small q, sorry. Well, let's take a time derivative of this. Because q depends on time, I have to use the chain rule. And I depends on time here, so I got to use the chain rule. Okay. Let me simplify this. Now what's I? I is dq dt. Right? I is dq dt. So I get q over c dq over dt plus dq over dt di over dt equals 0. But di dt is the second derivative of the charge. Since this equation has these two terms in common, I can cancel them. And I get, I forgot my L. Let me isolate the Q. And I get this equation, and my goal is to solve for Q as a function of time. I'm not sure why everything's blurry. I apologize for that. So now we have an equation for Q, and the goal is to solve for Q. I guess I'm not understanding your question. How do I know that to do dq dt and di dt? You mean how that I should take a derivative? How did it go from here to here? Well, I'm taking, let me use a better color because, I don't know, everything seems blurry. I have to use a chain rule for that, right? Q is a function of time, so I have to use the chain rule. So if I use the chain rule, I'm going to get 2Q times dq over dt. That's the chain rule. I just applied that. And I do it for I too because I depends on time. Okay. So when you look at this equation, yeah, I didn't write the Q as a function of time because I don't have space. Sorry, Morgan. So I really, you would think, okay, I have to integrate this twice to get Q, but I cannot do that because I don't know what Q is as a function of time explicitly. In fact, what I need to do is figure out what Q is as a function of time. That's what this equation gives us. This is a Math 33 problem, but we can all solve this one without really having to take Math 33. Because when you look at this, what does it tell you? It says what function I can differentiate twice, get the same function back, times a constant. It's sines and cosines. Right? I can take the derivative of a cosine twice and get a cosine back. And a negative in front of it too. By the way, you might be wondering why I chose to write it that way. It's just out of convenience. I can always write Q. There's a lot of ways I can write Q. I can write Q this way. Or I can write it this way. And out of convenience for us, we write it this way. In fact, I'll call this Q sub m. These are to be determined from initial conditions. These are to be determined from initial conditions. This is more convenience because you can actually look at the phase shift. It's hard to see it here. So we generally write the solution this way. You can also you can also make this a sign. You can make this a minus sign. There is some ambiguity as to how to write it, but there's many ways to write it. But you can also always show the equivalency of all these different versions of the sines and cosine functions. Okay, so I'm going to choose to write it this way. And of course, if I differentiate this twice, I get an omega squared out of it. The omega squared is basically 1 over LC. And so omega is 1 over the square root of LC. Okay, omega is 1 over the square root of LC. Okay, so let me continue. And we call it the angular frequency. And LC, and I should write down, hold on, give me a second here. Since this is a frequency, omega is 2 pi times the frequency, then the frequency this represents the frequency in which the energy is transferred between the capacitor and the inductor. So notice Q varies sinusoidally with time. What if we had a resistor? What if this had resistance in it? What would happen to it? What would happen in the non-ideal case? Well, in the non-ideal case, if we had resistance, energy would be lost as the energy is oscillating between the two. And so instead of an oscillating function, you'll have a decaying oscillating function. And how much it oscillates really is going to depend on how big the resistance is. Now, the current is just a time derivative of the charge. So it's omega Q sub m sine omega t. All I got to do is take the derivative of the cosine function. Now, if my initial conditions are that the charge is maximized, which is really what I had here, and the current is 0 when I open the switch, then my delta ends up being 0. I mean, think about it. If I put t equals 0 here, if Q equals Q max at t equals 0, then delta, that must be true. And of course, the derivative of that is going to give us a sine function. And so the current and the charge are 90 degrees out of phase with each other. The minus sign means that the capacitor is discharging. Now, what about the energy? We talked about the energy, and I kind of already said this about the energy, that the total energy is conserved, and that when all the energy is lost in the capacitor, it all goes to the inductor, and when the inductor loses all the energy, it goes to the capacitor. Which means then that the maximum energy stored in the capacitor has got to be equal to the maximum energy stored in the inductor. And so you can set an equation, Q squared max over 2C has to be equal to 1/2 Li max squared. So that's how the LC circuit works. The energy oscillates between the two. But what if we have an inductor? I'm sorry, what if we have a resistance in the circuit? What if it's a real circuit that has resistance? Then what? So I'm going to probably go a little bit over time, but I want to talk about really the part that we're skipping in the lab. Suppose we have a resistor, a capacitor, and an inductor in the circuit. And I want to look at the current in my circuit as a function of time. The graph I have there shows you the charge as a function of time. But I want to look at the current as a function of time. What's the current going to do? What's the current going to do in my circuit? I know that at t equals 0, because the inductor, because the inductor opposes the change in the current. Yeah. And at t equals infinity, I is also 0. So most likely, if I plot current as a function of time, the current will start at 0 and maybe do something like this. Or maybe the current will start at 0 and then decay exponentially. It just depends on how big that resistance is. So I'm either going to have an exponential decay in my current, or I'm going to have an oscillating exponential decay. Somehow I'm going to have some sort of exponential decay in there. And if I plot Q as a function of time, at some point, Q is going to reach a steady state because at some point the capacitor will be charged. And so you're going to get something where you might get oscillations about some steady state position, or you might get something like this, which you see in the graph. Or you might get something like this. Okay? But I want to focus on current. And so let me apply the modified version of Kirchhoff's. The reason why I say modified is because of the inductor. I'm going to assume, the current's going to be going this way, and I'm going to assume voltage drops in that same direction. And since I am doing that, then I can say I have a voltage gain here, and all these are voltage drops. This is the voltage drop across the resistor, the voltage drop across the capacitor, and then the voltage drop across the inductor. Look, I'm interested in the current, okay? Yeah, my drawing was poor. I'm sorry, Morgan. I overshot it. I'm interested in the current. I can solve that for charge if I wanted to, because this is dq dt, and this is the second derivative of q with respect to time. I'm interested in the current, so I want to solve for the current. In order for me to do that, I need to have I's everywhere. So guess what I'm going to do to my equation? And it's perfectly legal for me to do this. I'm going to take the time derivative of the equation. So it's going to, so I'm taking time derivative of a constant, that's 0. And so I'm going to have the time derivative of this the time derivative of the charge is the current, and then the time derivative of this okay. I'm going to cancel minus signs, and I'm going to divide both sides by L. This is a second order differential equation with constant coefficients. Math 32 problem, 33 problem. So what do I do now? So I know the reason why I drew the graphs, and I probably overshot it, and I apologize for that. The oscillation should go to 0, and I overshot it. I'm drawing quickly because I'm running out of time, sorry. I know I'm going to have that or some kind of decaying exponential. So I'm going to do the following. I'm going to guess that I as a function of time looks like this. Where I have to figure out where omega is. So what I'm going to do is I'm going to take this guy and put it into my equation. So I'll put this thing into my equation. And I'm going to I'm going to take a look at this real quick because I want to skip. I'm going to try to skip a couple steps if I can. If I take the derivative, second derivative of this guy, this thing here, don't I get this function back times omega squared? Think about it. If I take the derivative of this term with respect to time, don't I get the function back times omega? And then here I have the same function again. So really every term is going to have the a e to the omega t. It's just that this term will have an omega squared in it. The second term will have an r over L omega. And the third term and I can use a solution as long as the thing in brackets is 0. As long as this thing in brackets is 0, I can use the solution. So that means there's some conditions that are set on omega. So let's figure out what they are. Well, I use the quadratic formula. There we go. Let me factor out the 4 from here. Okay. I'm going to factor out the 4 and rewrite over here. Since there are 2 values of omega that come out of this, I kind of have to rewrite my solution that contains both values of omega. So I'm going to erase the board. I'm going to write my solution. I'll write it big. Oops. And A and B are constants we determined from the initial conditions, and I'm not interested in them right now. Let me factor out this term. It's a lot of writing. Okay, so there's my solution. But there's some things I got to consider. Interesting cases I'm going to consider. Look at the radicals up here. What if this is the case?
Well, if this is the case, if R over 2L is bigger than 1 over LC, this term is bigger than this term. The radicals are both, what's under the radical are both positive, and so you have this term which is exponentially grows, but then is multiplied by this term which exponentially decays. So overall, this term represents an exponential decay because this exponent is bigger than this exponent. This is more negative than that is positive. And then this one's negative and this one's negative. So you get a decaying exponential overall. So what you get is the system reaching the steady state. So system reaches a steady state with no oscillations. So if you were looking to charge, the charge would exponentially grow until you reach its maximum value. Now what about this case? Now what? What happens? Remember, Morgan, I factored out, remember what I had here? And I specifically said factor out to 4. Because if you have factor out to 4, you get a 2 over here. And then you have to get a 2 over there. Okay? And there's a 2 here. So I went from here to here. I did it in one step because of time. But I said that if you factor this out, that you get a 2 down here and a 2 out here. Okay? So what about this case? I'm not sure I get, you're talking about this guy squared? Okay, we'll go through it then. So if I have this, I pull out the 4. Okay, all right, good. So now, if this is less than this, then this radical is, oh, what do you do? Now what happens? I'm taking the square root of a negative number. I have to rewrite this. The square root of has to be written this way. And so my solution looks like this. Oops, doesn't look like that. So what are these? Oh, I guess I should say this then. Sorry. That's my bad. Thanks for pointing that out. Okay, that was my bad. That's because I'm rushing. Sorry. Yeah, because I got to compare this term to this term, not this. Because otherwise, I got to compare the square root. I got to compare this to the square root of that. Okay, so we're fine then. Sorry about that. Okay, so what are these then? What do they represent? You got to remember, and you might not know Euler's formula. I mean, Euler's formula is this. These are sines and cosines with an exponential decay in them. So you get a sine, you get an exponential decay with a sinusoid. So you're going to get a system reaches steady state with oscillations. Okay, I got two more things. I'm sorry it's taking so long. I'm trying to go fast as I can, but of course I make mistakes as I'm going fast. The last case is this. Now what? This is 0, and that's 0. I get a double valued solution. And what you'll learn in DE, that there's a technique, and I'm not going to go through the technique. You can show that the second solution, I forget the name of the technique. Is basically exponential multiplied by t. I'm showing you without proof. But in this case, this is called critically damped. And so you get the fastest, or the system approaches steady state in the shortest time. So this bottom one is called critically damped. This one is called underdamped. And this one's called overdamped. Now, when you take 215 and you do the simple harmonic oscillator problem, you're going to encounter this. You're going to have a mass on a spring, and then you include damping. You will have solutions that look exactly like this. When you take 215, the math that we're covering in chapters 32 and 33, you will see in 215 again. Okay, it's the same math, different problem. Same solutions, different problem. Okay, all right. I'm sorry, one more thing. I got to show you the underdamped case. So over the summer, when I was developing this lab, of course I had to take data in order to make sure that the lab works. So I did the underdamped case, which is part 3 of your lab, which I'm skipping. And all you would have to do in part 3, you wouldn't have to take any data. All you got to do is show that you can do the underdamped case. So I used the scope, although it's essentially the one you guys used. And I hooked up the underdamped circuit, and I put in a square pulse, and there is what I observed. And there you see the oscillation. Now, it is possible for you to observe it, but I didn't want you to waste of time doing this. In your kit, you have a potentiometer. The problem with the potentiometer that you have is it's really coarse. If you adjust the potentiometer, if you can actually adjust the potentiometer so you set it to 25 ohms across the middle terminal of one of the end terminals, you can get this to work. But that potentiometer is so coarse, it's only one turn. It's really hard. It goes from 0 to 1,000 ohms very quickly. So yeah, if you set up the circuit, the RLC circuit with around 25 ohms and your inductor that you're given, you can probably observe it. It's just that potentiometer is so, the turning is so coarse on it that I decided, okay, let's just skip this part. Really what we need is a 10 millihenry inductor, then you'd be able to see it. This data that you see was taken with a 10 millihenry inductor. It's the same scope except yours is black. Okay. All right, I apologize for going over and rushing too fast through the equations. Okay. So I just wanted to show you this because the next chapter I'm going to solve a differential equation in which there's 2 solutions. One of them is the one I just did, and then the other one will be the steady state solution. Okay? All right, so anyway, have a good weekend. If I don't see you in 2 10 hours, sorry again for going so far over.